This is the UE1, my 1-bit vacuum tube homebrew computer that I've been building from the ground up for about 3 years now. This project's been going on way too long, and it's time to wrap it up and call it finished so we can move on to bigger, better, and badder things. And we are so close to being done with this thing that I think we might actually be able to get there in this video. If I could turn it on. You see, the problem is that Texas decided it was ready to be very, very cold outside. And I've had the heater running in this room all morning, and it's still only up to about 17 Celsius or about 60 Fahrenheit in here, which might be too cold to turn this thing on without overloading my power supply. And I realize that doesn't make a whole lot of sense because it's a vacuum tube computer. It's going to be emanating heat at a ridiculous level, and this could actually warm the room up to a pretty comfortable temperature. But inside of each one of these about 350 vacuum tubes is a little filament. And filaments are very interesting because as they get hotter, their resistance goes up, which is an excellent property. It's kind of a self-regulating thing, so that the hotter it gets, the higher the resistance becomes, limiting the amount of current that'll go through it, which then reduces the temperature a little bit until it finds a nice, beautiful little equilibrium. However, the inverse is true. The colder they get, the less their resistance becomes. And when it's very, very cold in the room, their resistance is going to be so low that the power supply is going to see it as a dead short, particularly because it's trying to power up all of these at the same time. So I need to get the room warm enough to power this thing up and get the tubes warming up. And then once the tubes are starting to warm up, I need to keep the room cool enough so it doesn't overheat. Nobody said vacuum tube computing was easy, but I think we can get the room warm enough so I can power this thing up and we can start testing out a couple of things. But if you're chiming in on this episode, the very last episode in the series, it might be a little confusing as to what exactly it is that we're looking at here. So while I let the heater do a little more warming up of the room, I'm going to give you guys a quick rundown of what works, what doesn't, and what kind of output we're expecting to see out of it so that we can confirm that it is actually working. What we've built out of vacuum tubes over there is essentially this. This is the minimal ICU system as outlined by Motorola in the MC14500 handbook. The MC14500 is a 1-bit industrial control unit that Motorola designed in the 70s to replace relay ladder logic in industrial situations like traffic light controllers and turnstiles and things like that. And I figured that having a 1-bit microprocessor would make a perfect platform to try and recreate out of vacuum tubes for my very first homebrew computer ever. So what can you do with a 1-bit processor? Not a whole lot. The minimal ICU system here that we built is really just a demonstration system for the Motorola chip. I essentially recreated this, but I didn't like the logic unit that they put in that, so I upgraded that to a full-fledged arithmetic logic unit. That thing can do addition and subtraction now. Looking above the Motorola chip here on the block diagram for the minimal ICU system, we have an 8-bit ROM that is being fed with an 8-bit address coming from two 4-bit binary counters. That 8-bit ROM provides an 8-bit value out. Half of it is being used for an instruction for the Motorola chip. The other half is being used as a memory address. And I have pretty much replicated exactly this, only I didn't do it with a ROM. I wanted to be period correct, so I built it out of a paper tape reader. And we built the paper tape reader completely from scratch, which is why it's pretty janky, but also, hey, it works. It's working. It's feeding 8-bit values into the system just fine. Now, here on the bottom, we have our memory. We have on the left system inputs, in the middle it says system outputs and scratch bits, and then on the right system outputs. Now I changed these system outputs and scratch bits a little bit. I don't have an individual output coming out of them like they show here, so it's just a scratch register. I have 8 bits of random access memory. The system outputs, these are write only. I can write a value to them, but I cannot read that value back within this system. And the 7 inputs are effectively read-only. And they're coming from 7 toggle switches that are up in the top, but also I can tie right into the header and have an external input be able to be read through these inputs here. So that is pretty much every single block on this diagram represented on the wall over there out of vacuum tubes, which is pretty wild. And like the large majority of it works. In the previous episode, we were executing instructions, we were halting correctly, we were ringing the bell. The only thing that wasn't working in the previous episode was our scratch register, and our output register did not seem to be latching values correctly. But I went back and reviewed the footage, and I think it's trying to. I think we have a situation where about half of our bits are working correctly and half of our bits are not. And that is 100% my fault. It comes down to how I designed the memory cells. I was trying to be cheeky and smart here and save a tube per bit. And so instead of having a full-fledged 6AU6, I slipped a 6977 in there, which is a vacuum fluorescent display. Yet I've coupled these two together to make a flip-flop, which means it's an incredibly unbalanced flip-flop. And I did get it to where every single bit was flipping and flopping exactly like it was supposed to on the bench. Once it's bolted to the actual thing with voltage feeding into it from everything else, things are starting to misbehave. And I think this can partially be attributed to a power distribution problem. The power comes into the top and then runs down the side where it then gets fed into all the different things. And it has to go through a bunch of these interconnection PCBs that I've made that allow me to connect different parts of the modular design to each other. But those connectors are not the best for power delivery. And I'm afraid that by the time the power makes it to the memory, it's not a clean plus 24 volts anymore. It's maybe down to like 21 volts, something like that. And that's gonna throw the balance of that 6AU6 and that 6977 out of whack. And it may not be flipping and flopping like it's supposed to anymore. So I think what we need to do today is focus on getting better power delivery going on. And I have some ideas about how to tackle that without destroying the modularity of the design and the repairability of everything. And hopefully that'll solve some of our flip-flop issues down there. And if the memory is working at 100%, that thing will be finished, which is the goal for this week. I hope we get there. So let's just get started. Hopefully there's not too much left to do to get this thing humming along, but we're gonna start with trying to get some better power distribution going on. You can see that at the top of the board where power comes in, we're sitting right at 23 volts. If I then check it again, but at the bottom on the memory boards, we're only managing 21.9 volts. That's not a massive drop, but could be enough to upset the balance of my flip-flops. Moving over to the processor board, at the top I'm measuring 22.1 volts, which is honestly a lot lower than I was expecting. At the bottom of the board, I'm measuring 21.17 volts. So in short, the voltage on the processor board is a little low overall, and we're seeing about a 1 to 1.5 volt drop from top to bottom on both boards. Let's see if we can fix this. I want to retain the modularity of the design, so I'm going to solder long wires that go from the upper harness connector down to the lower harness connector. This way there is a solid core power wire delivering power to the top and bottom. It's not a perfect solution, but it should help distribute power a little more evenly without permanently attaching any board to another board. I'll do this for both the left and right sides, and for the memory board here, I'm running multiple wires per voltage rail. It's a little finicky to make sure I got them cut to the right length and soldered in place, but ultimately I got the wires run and am able to pop the connectors back in place. I only showed one side here, but I did the same for the left and right of both the memory and processor boards. Next, I want to adjust the output voltage on the Meanwell supplies. They have a little potentiometer for dialing up or down the voltage, and after a little twiddling, it comes right up to just about 24 volts. Checking the voltage level on the memory cards now, that's a much nicer 23.5 volts evenly distributed. Looks like our distribution wires work like a charm. But even though we now have clean voltage, the memory is still misbehaving. And so began hours of single-stepping through instructions one by one, hoping to narrow down on any specific fault. Okay, sit rep. First of all, it's my first ever homebrew, but like it's a bad design. It is not good. Next time we will do much, much better because this is embarrassingly bad as the more I troubleshoot it. Like I'm like double buffering stuff and it's just, you can tell that I changed my mind like 15 times in the middle of designing it. And anyways, we're just gonna try and get it going. I think we can. I think it should be working, but I've discovered some pretty interesting problems. First and foremost, this toggle switch up here, which I'm using on my kind of single step panel, is not providing a good plus 24 volts. It's like providing like plus 14. So it's got a high resistance connection in there somewhere. Could be a bad solder joint. Could be the toggle switch itself is going bad. They're like toggle switches from the Soviet era. So, you know, we're asking a whole lot of them. Next, there is without a doubt a bad vacuum tube right around in here. I'm pretty sure it's this one. The way this works is that we have the address signal come in, and in this case it's address 1. It comes in, gets buffered, then gets inverted, and then the inverted signal gets buffered again. Now I can see that it's getting buffered correctly and I can see that it's getting inverted correctly, but the inverted buffered signal is just like permanently stuck low. It's not actually buffering it. And finally, we have, I think, a bad either inverter up here or buffer up here, because the logic low that's coming out of that should be at about 2 volts, and I'm seeing it at about 5 to 6 volts. And that should still be low enough to be considered logic low, but I don't know, it could be that these are kind of finicky and sometimes they pick that up as like a mid-range signal and things go chaotic. So we need to double check the inverter and buffer up here and make sure that it's getting a proper logic low coming out of it. We need to fix our switch and we need to replace the bad tube here, and hopefully that gets things a lot closer. Let's start by figuring out that bad toggle switch. Without the ability to single step correctly, we're in a really rough spot. After pulling the diagnostic board and getting it on the bench, I'll use some soldering braid to wick up the solder on the legs of the switch. And this MG Chemicals braid works so well, the switch just pulls right out, no problem at all. Hooking it up to my multimeter, yeah, look at that, no continuity ever. That is absolutely a cooked toggle switch. Thankfully I have a spare, so I'll just toss it in place and solder it down nice and tight. With the diag board back in place, I'll use the multimeter to confirm which tube is bad on the address buffer board. Once I've located it, I can just pull it out of the socket and then slot in a new tube and problem solved. Finally, I need to investigate that tube that's weak up top here. With no light on it, it should be around 2 volts instead of 5 volts. But even after adjusting it a little, it still didn't clean up. Ultimately, I swapped out both the buffer tube and the inverter tube of the bit in question, and that helped considerably. Then it was right back into more single-step troubleshooting. At this point though, I'm in a pretty good spot. I can deposit values into every bit of memory, with the exception of this one little bit right here. I pulled out the multimeter and did a lot of testing and information gathering, but no matter what, I couldn't make sense of the numbers I was seeing until it dawned on me. I've got it all wrong. I'll explain more on what's going on here in a second, but once I figured out what was up, I moved on to trying to get the tape reader to play nicely again. First, I made new guides to keep the tape going in the right direction. Then I punched a tape that was all ones so I could check the timing of the clock versus the data bits. With the scope out, I did indeed still have a lot of adjustment to do. All right, it's been like 12 solid hours of troubleshooting and like tracing wires and trying to phone past me and ask him what the heck he was thinking. But we started this episode with me talking about how cold it is, and here I am in short sleeve shirts because this thing is currently on running and just blasting heat out like a furnace. And you know what? I'm gonna call it. I'm gonna say that UE1 is done. It is functional. Mostly. I mean, I'm really excited. This is like a 3-year project and we got there in this episode. But there are still some problems. Whenever I was running it off of the tape, I noticed that I was not getting clean memory addresses coming into the memory down here. And when I went through and looked at it up here, I could see that these 2 bits right here were not toggling like they should. And it turned out that they had too much direct light on them. It was kind of blasting through the paper whenever the paper was supposed to be giving us a logic 0. And you guys mentioned this, and I knew it had to happen. I had to cut a little piece of plastic to put it on there to kind of diffuse the light. The plastic came from one of these, a little deck tape case. Don't worry, the deck tape itself is still totally fine, but the case donated a little bit of plastic to the project. Once I did that, I got a lot more even illumination on all of the photodiodes, but I had to go through and readjust every single potentiometer again for the new light level and the new kind of diffusion that was going on. Once that happened, bam, the whole thing sprung into life. And check this out, let's hit go. It's gonna run through the tape. We get lots of little flashing down here. Comes to a halt perfectly. It just ran all of that code completely perfectly. But there are two problems that you may have noticed in that. And there's one that kind of looks like a problem, but in actuality isn't. Whenever it's running, the lights down here look like they're flashing just on and off. And that's because this thing's actually executing code too fast for the human eye to keep up. When I filmed it at 120 frames per second, you can see that the output register is filling up and emptying out exactly like it's supposed to. It's doing it completely sequentially. That means it's executing code, writing to memory, 100% working, except for this single little bit right here. You'll notice that that bit never clears. And I spent a lot of time trying to hunt down why that bit never cleared. Turns out it's absolutely nothing wrong with the memory. The memory's working fine. I made kind of a mistake when I was wiring this up. The thing is that this bit sits at memory address 1000, and I wanted memory address 1000 to do double duty. Whenever you read from memory address 1000, I want the result register to be looping back because that's an incredibly powerful operation. Whenever you write to memory address 1000, I wanted you to write the value into this bit right here, which is the bit that is not toggling. I think you guys can see what's going on here. Whenever you do a write, the memory or result register is still looping back around. I didn't design it correctly. That's like a straight up design fault. But it's important to know that really we only have a problem with this bit when the results register is storing a 1 and we're trying to do a store complement instruction to memory address 1000. Every other operation, every other memory address is working perfectly. It's only in that really kind of niche example that it doesn't work like it's supposed to. So I'm gonna call it a feature, not a bug. The other problem that you guys may have noticed is that when it ran, the bell didn't ring. And that's because the bell kind of has a mind of its own. This little PCB that I made here with the 2 thyrotrons and the relay, it works perfectly on the breadboard. I've tested it multiple times. It does exactly what I want it to do. But when it's here on this PCB, it has a mind of its own. It'll start ringing and then not stop ringing just without even executing any instructions, just when it's sitting here completely static. But when it's not ringing, if you run it, it does ring the bell perfectly fine. So the circuit is so close. There's just something wonky about it. And that's something that I can fix off camera. Not a big deal. I think the circuit's mostly fine. I probably just got something set up slightly wrong. Maybe a couple of resistor values or something like that need to be shifted around. It's just something that I gotta sit down and figure out. But everything else is working at 100%. This thing executes code, stores it in memory. This is a functioning homebrew computer. My very first homebrew computer, the UE1, is now done. How awesome is that? Like a 3-year project coming to completion. It's so good. Oh, I'm so happy. There's a lot, like I said, there's some more little things that we need to do with it because no project is ever truly done. But this project is now finished enough that I am comfortable moving on to the next homebrew project that I want to build. And it's gonna also be vacuum tube based, but I'm not entirely sure which direction we're gonna go with it just yet. It's certainly gonna have a wider data bus than 1 bit. But I want to thank you all so much for tagging along with me on this insanely long project. It is now finished. I am beyond happy, and I hope that I can see you guys in the next episode.